Good morning, class. We are looking at section 4.8, Newton's method. We have covered various sections, and the last one was 4.7, optimization problem, in which case we basically said we are looking at normally an open interval. There is only one critical point, and that when we go through the first or second derivative test becomes not only a local, also an absolute max or mean. Okay. Now the idea of Newton's method is very simple. When you are looking to find a root, a zero of a function, okay, Newton noticed that excuse me, the tangent line close to the root crosses the x-axis nearby. So when we look at this case, okay, if you are interested in finding this is the zero of the function. So if we draw a tangent line nearby, for example, a point which its x-coordinate is not a zero of a function, but it's nearby. If you draw a tangent line, the tangent line crosses the axis somewhere else, but that point is close to the actual x-intercept. So I want everybody to see this concept. So one more time. So you have a function, you want to find the x-intercept, this point. If we happen to have a point nearby, we draw a tangent line. That point doesn't have, is not the same as the x-intercept. However, the tangent line crosses the x-axis somewhere near the actual x-intercept. So we can find the equation of this tangent line and then find the x-intercept, and with the same x-coordinate create a new tangent line, and we keep up with that process until we get to the actual x-intercept. That was the idea behind this. We are going to use the equation of a tangent line. How? Everybody remembers the point slope. Again, it's the good old point slope. So with that being the case, y minus y1 is m times x minus x sub 1. All right. So this is the first point, okay? Somewhere here, again, clearly x sub 1 is not an x-intercept. Draw a tangent line. And let's calculate the equation of a tangent line using the point slope. Y minus y1, okay, equals m times x minus x sub 1. So if this point has x coordinate x sub 1, the y coordinate must be y sub 1 or f of x sub 1. So y minus y sub 1 or f of x sub 1. And the tangent line m is f prime of x sub 1. So we have all of that, okay? So that's the equation of a tangent line in point slope, okay? Now, if we set y equal to, so this is the equation. This is a general equation. If we set y equal to 0, we can find the x coordinate for the x-intercept of this tangent line. So let's replace the y with 0 and solve. Notice what happens. You can replace the y with 0, divide by f prime. I hope everybody can see. So this is replaced with 0. We divide by f prime, we get x minus x sub 1. So we move the negative x sub 1 becomes positive x sub 1 on the other side. This x is the new x-intercept, okay? For what? This is the x-intercept of the tangent line, okay? And so x sub 2 is the new point that we are going to deal with. X sub 2 is x sub 1 minus f of x sub 1 over f prime of x sub 1. So from some point, we got a new point. That new point is the x-intercept of the function? No, it is the x-intercept of the tangent line. When we continue with the process, okay, we come up with the methodology known as the Newton's method, okay? Newton's method. That's the idea behind that. And so the next one, x sub 3 equals x sub 2 minus f of x sub 2, okay, over f prime of x sub 2. And you move on to the next and to the next. And now, in general, we say f of x sub n plus 1 is f of x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. In other words, if you want the next point, you start with the previous one minus the function goes at top, its derivative goes at the bottom. Okay, so this is the process known as the Newton's method. Now, take a look at the concept by looking at the various graphs. So this is the general Newton's method. Okay, so you are looking for this x-intercept on the function, graph of the function, okay? So you draw some tangent line nearby. So this is your first point and this is your next point. Now this next point gives you another tangent line that is going to give a x-intercept closer. So take a look at the initial one, x sub 0, okay? And we draw the tangent line. And then that is the blue one. And it creates a new x-intercept for the tangent line, and therefore a new point on the function. Now you draw a second tangent line, the green one. Notice x sub 2 is closer to the actual 0 of the function than x sub 1. And so that's the idea. You start from some point and you get closer and closer. So in a limiting sense, when you take the limit as n goes to infinity, it becomes the actual point of interest. Now, I'm going to give you this for the sake of doing the homework that takes long. This is a simple programming if you have a graphing calculator, or you can even use an emulator online to just speed up the process. You have to show your work for a couple of them for practice, because on the exam you want to show work from A to Z. But if you have to have it done 7 times, that is going to be tedious, long, and takes forever to actually do the math. So I'm giving you the formula. First, you put y1 equals f of x, then y sub 2 equals f prime. You store x sub 1, the point that you begin with, into x, and then x minus y sub 1 over y sub 2, you store it in x, and you enter repeatedly. It gives you the next one, and the next one, and the next one. It calculates them for you. In other words, we are looking at the graphs that give us ultimately the actual intercept. I hope everybody's comfortable with that. Let's get started with a basic example. All right. Starting with some point, in this case, it's given to us x sub 1 equals -1. We want to use this method, Newton's method, to find the third approximation, okay? And so let's see what's happening here. We are given the third approximation to the root of this equation, x to the power of 7 plus 4 equals 0. And we want 4 decimals. By the way, if the number of decimals is given, so be it. If not, you want to go with a lot of decimals to be on the safe side. So what is the function? The function is this one. The function is f of x equals x to the power of 7 plus 4. So immediately when we look at this formula, we need f prime. Okay, so let's come up with f prime, which is 7x to the power of 6. And we also need to start from somewhere. They said from -1, and so we can go with the next. Okay. Now, using the formula, we can replace the f with x to the power of 7 plus 4 and f prime with this one. So we can rewrite it in this fashion, class. We are looking at this formula, everybody. We are looking at this formula, okay? And we are replacing f of x sub n accordingly. So we're going to write x sub n to the power of 7 plus 4 and so on and so forth. Now, if I want x sub 2 on the left side, on the right side, all the n's are 1. So this is x sub 1, okay, class? All right, what is x sub 1? -1, so let's plug it in. -1 here minus -1 to the power of 7 plus 4 over 7 times -1 to the power of 6. Okay. So obviously this becomes -1 with 4 becomes +3. This becomes +1 times 7 is 7. So we have the following -1 minus 3/7, and we get -10 over 7. Now we repeat the same thing. Now here's what I want you to notice. Getting the first one, the second one, a couple of them is not difficult at all. But if you want to get 7, 8 of them, it becomes difficult, class. So take a look at even the next one. We were dealing with a nice and easy number, -1 as x sub 1. Now x sub 2 is not as nice, okay? So, and that's my point. So you go to this formula again, and now you want x sub 3, and the previous one is -10 over 7. So this x sub n is now -10 over 7. So take a look. And so what happens here, this calculation is a lot more difficult to do it in the head than x sub 2. X sub 2 was fairly decent and easy. X sub 3 is not. You have to do it with the calculator. And that's why I said, as long as you can show this step, you must show this step, okay? You must show this step. And then you show 1 and perhaps 2, then who cares? 4 more or 5 more or 10 more, you can do all of them. It's not a problem. So you want to show to your reader that you know the function, you know f prime, and where you begin. And the general formula that you are going to create based on this function f of x and f prime of x. And so you show a couple of steps and the rest is simple. Here's another example. Okay. We have the function f of x equals x squared minus 2. Everybody knows that's a parabola y equals x squared shifted down by 2 units. And we want to start with x sub 1 equals 1 as the initial guess. Sometimes it's not given. Okay. And we want to calculate 3 iteration. That means we want to calculate 3 more. That's what it means. This is x sub 1, then 3 more, x sub 2, x sub 3, x sub 4. So we need to go through the process. And what this means is you have f of x equals x squared minus 2, f prime equals 2x, and you are going to start with x sub 1 equals 1. So here's the graph. Here's x sub 1 equals 1, okay. And look at x sub 1 equals 1 on the graph of the function and the location. And right then and there, you draw the tangent line. Again, I wanted you to see this so you understand how the Newton's method works. So you are starting with the x-intercept? Absolutely not. What are you starting with? Somewhere nearby. From that point, you draw a tangent line, okay? And the tangent line, notice, gives you this point, and that's what we are looking for. So we calculate the equation of a tangent line, we set y equal to 0, and it gives us the x coordinate for this point. That is the Newton's method. That's it. Okay, so now what is x sub 2? So that means this is replaced with 2 and this is replaced with 1. This is x sub 2 now, class. What is x sub 2 equal to? This formula. And again, I hope this is a good illustration as to precisely what Newton's method is all about. Okay. Replace the x sub 1 with 1. Okay. 1 minus f of 1 over f prime of 1. All right, so what is f of 1? We put 1 squared minus 2, which is negative 1. What is f prime of 1? 2 times 1, which is 2. Okay, so you plug in and you get 1 plus 1/2 or 1.5. Now this is x sub 2. All right, so what is x sub 3? It's x sub 2 minus f of x sub 2 over f prime of x sub 2. So take a look. So x sub 2 becomes 1.5. From 1.5, we figure out the point on the graph of the function having the same x coordinate, namely 1.5. And here's the new tangent line now. And as you can see, this new tangent line gives you a new x-intercept for the tangent line, which is closer than the old one. Now we use now 1.5. So you have to calculate f of 1.5, which is 1.5 squared minus 2. Okay, 225 minus 2. And f prime of x is 2 times x or 2 times 1.5 or 3. And do the math. This is now doing the math, resulting in 1.416667. So the x sub 3 is that, and we calculate in the same manner. Now we plug in, so we are going to go with x sub 4. This becomes x sub 3. So now replace this number in there. And I hope you see the next one is a little bit harder because the number is more involved. And you come up with the answer. Now, what you'll notice, and this is what is important, that these numbers are getting closer and closer. If you compare, for example, these two, the first 2 decimals are the same, the third decimal is not, okay? So that is telling you that they are getting closer. And if you continue, the next one is even closer, and maybe a couple more, they actually give you the intercept. So that is the meaning, class. I hope this graph explains precisely what's going on. So if you look at this one more time in slide mode, step by step, you understand how this Newton's method actually works. Okay. Here's the next one. We want to estimate the point of intersection for the following functions. Y equals tan x, y equals 2x. And by the way, I put the formula for the Newton's method as well as the programming here. Okay, you can program this into a calculator. All right, so let's see what happens. If you want to find intersection, you have to set the two functions equal. Remember that, right? Okay, so when you do that, then you bring the 2x to the left or tan x to the right, and you call that f of x. So setting this equal to 0, it means coming up with f of x being one side. Again, before we come up with that, class, let me just show you quickly. When you get here, it doesn't matter 2x goes to the left or tan x goes to the right, then this is a function that you're dealing with, and obviously f of x is tan x minus 2x. and f prime is secant squared minus 2. Everybody remembers the derivative of both cases. So you have to start from somewhere, okay? And if you don't know, you can just guesstimate, or you can sort of use a graph to guesstimate where to begin. If we are doing this by hand, we really should be close or it goes crazy, okay? If you're doing it by, the programming that I showed you, as long as you can show your readers, here's what you did. You came up with the function, okay? You set them equal. You came up with the function, you differentiated, and now this formula, okay? And starting from somewhere, then you'll be fine. So we start from either 1 or 1.25. Again, without a calculator, 1.25 would be better. You may not know that. Just stick with an easy number, 1. Start with 1. By the way, when we say 1 is in radians, okay? Just to give you an idea, again, where you begin if you don't know. When x is 1, okay, you're dealing with tan of 1 radian. Remember, 1 radian is about 60 degrees. So this is about square root of 3, and this is minus 2. So just to give you an idea, if you go with 1, square root of 3 minus 2 equals 0. It's close. Is it 0? Absolutely not. Okay. Is it the square root of 3? No. I'm saying it's close because 1 radian is about 60 degrees, and tan of 60 degrees is square root of 3. Okay, square root of 3 is about 1.71. So that's a close number. Number 1 is close. This is even closer. Again, you can stick with 1 and start with that. Now let's write the formula, okay? Using this, let's write the formula. Simply put f of x sub n, so x changes to x sub n. This is what you have. So if you're starting with 1 or 1.25, you just put it in. So x sub 2 equals x sub 1, which is 1 or 1.25, minus f of 1.25 over f prime of 1.25, which means tan of 1.25 minus 2 times 1.25, 1 over, by the way, secant, for the sake of calculation, secant is the same as 1 over cosine. 1 over cosine of 1.25 squared minus 2. Okay, and this requires obviously a calculator. You come up with the answer. Now you repeat the same thing. So x sub 3 is x sub 2, which is 1.18675. And notice how tough it's going to be if you're going to just keep on doing this by hand. And then tangent of that minus 2 times that, 1 over cosine of that squared minus 2 gives you the next one. Now, just to give you an idea how far we should go, let's go back to the question. We want to use this method to do what? To come up with an approximation such that 1, 2, 3, 4 decimals, 0.0001. So they differ by less than that. So obviously, first look for 4. You see, even the second one is different, so that's not good. Of course, they are sort of close, but not good. Let's look at the next one. And when you're looking at the next one, you compare x sub 4 to x sub 3. The first one, okay, the second one, so far. But the third one is not good. So that means they differ more than 0.0001. I hope you see that. You compare x sub 4 to x sub 3. Not good, not good. Okay, and here's the next one. Now compare these two. Okay, the first decimal is the same, the second one, the third, the fourth, and even the fifth one is the same, so that's good. By the way, if the fourth one, if the fifth one are not the same, you remember you have to do the rounding, okay? So you want to be careful when you do the rounding to come up with the answer. So if we want to find the point of intersection, these two show the difference of less than that number, Okay, so this is a good choice, which means if I choose the next one, it's even less than that. So this is good enough. Again, one more time. We are looking for a difference that is less than that. And this is the case here. So we don't have to go further. We choose this one as the x coordinate. And when we plug it into the equation, okay, y equals tan x. So tan of this number is the same as 2 times this number. And that would be your y coordinate. I hope everybody understands how we arrive at the y coordinate, okay? So simply go to tan x, y equals tan x. And I would highly recommend you do both because you want to make sure that both of them give you the same answer. Obviously, the second one is easier to use. Y equals 2x. It's just multiply by 2. That's easier. However, you're checking your work. You want to make sure that you haven't made a mistake. This tan x should give you the same answer. Okay, so that must be checked. Let me see if I can quickly show you a graphing calculator if I have this here. If I can make this large, this is as large as it gets, class. So first and foremost, y sub 1, I hope you can see that. Y sub 1, okay, let me just move this a little bit. Okay, y sub 1, take a look everybody, y sub 1 is tan x minus 2x or f of x. Y sub 2 is secant squared x minus 2, okay? So it's 1 over cosine squared minus 2. So that's the first thing, okay? And then over here, I put number 1 into x, I stored it, and then notice x minus y1 over y2, okay? And store it in x, and I'm clicking enter repeatedly, and it gives me the answer. By the way, I started with number 1 because of the luxury of a calculation, making it easier. So I hope you see that it can be done that way. Okay, class? Okay, so I started with 1 stored in x, and it gives you 1. Then x minus y1 over y sub 2 stored in x, and press enter. And as you come down, so from 1, we get to 1.3104783. Enter. You don't have to do anything. Just enter 1.223929096 and keep on going. Okay, keep on going with the numbers. Okay, I hope everybody can see what happened here. All right. So you can use a graphing calculator to come up with the answer fairly fast. All right. This is an interesting example. We have a graph, and we're going to start with some initial points, such as x of 1 equals 0. We want to see what happens to the Newton's method. And remember, the Newton's method, x sub n, okay, so let me just quickly write this too. So x sub n plus 1 is x sub n. That means the previous one. Minus f over f prime. And of course, x sub n, but it is important. I hope everybody can see that what happens here. I want to emphasize the denominator here. What is the denominator, everybody? The denominator is f prime. Generally speaking, when we draw the tangent line, things get better as long as we are not close to f prime being 0. That's really the idea. When f prime becomes 0, this becomes undefined and we get a worst case scenario. So I hope everybody understands why I'm writing the formula to refresh your memory about the formula and again emphasize what happens here. So having said that, if you start with x sub 1 equals 0, remember a 0 is here and here's the tangent line, okay? So I hope you see the tangent line, okay, is this. So if x sub 1 is 0, then x sub 2 is negative, okay, and x sub 3 is even more negative. So we are getting away, okay, from the, remember the intercepts, going back to the intercept is somewhere here and somewhere here, okay? So we want to get closer and closer to the actual x-intercept, and we don't. When x sub 1, when the choice is, now we are looking at part B1, remember, what do you have? Horizontal tangent line, just forget it, it won't work, okay? Because of going back to the formula, look at f prime, okay? It's the denominator. So if it gets close to 0, that is out. Let's go with the part C, number 3, okay? Now, so x sub 1 is 3 and x sub 2 becomes 1. So notice you draw it and 1 back to part B because the next one gives you a horizontal one, okay? So I hope you realize as we go to x sub 2 being 1, we are back in part B in essence. So that doesn't work, that fails. In other words, does Newton method work all the time? Of course not, and that's the idea, okay? If you choose 4, okay, 4 is another tangent line which is horizontal. Doesn't work, okay? If you choose 5, now what is 5? 5 is here and here's the tangent line. And that seems to be working. The point of this exercise is to show you that, okay, we learned about Newton's method, that's fine and dandy. Doesn't mean that it's going to work all the time. Sometimes it doesn't, okay? When would it not? If it doesn't converge, it fails. When it diverges, it fails. One of the reasons it may diverge is that the f prime is getting closer and closer to 0. And that's the main thing that is easy to see. I hope everybody is comfortable. We can use the Newton's method to find and approximate roots. For example, we've seen this by the method of differentiation and the linearization. Ultimately, it's very similar to that concept. So we want to find the 8th root of 500, and we want to use 8 decimals. That's something you want to be careful of. So what does it mean? We don't know what this is. We got to call it x, which means x to the power of 8 must be 500. So we are looking for the 8th root of 500. We don't know what it is. If we call it x, it is the same equation as x to the power of 8 equals 500. So it is the same as looking for the root of the function x to the power of 8 minus 500. So f of x becomes x to the power of 8 minus 500. F prime becomes 8x to the power of 7. So again, you want to show your reader step by step why this is f of x, why you come up with f prime. Okay, so again, you said this equal to x to the power of 8 becomes 500. This is the function, this is f prime. Why are we writing that? Because we are going to use this. So the point is, where do you begin? Okay, you have to begin with some number fairly close. I hope everybody knows that 2 to the power of 8 is 256, and that's fine. You can start with that because 3 to the power of 8 is 6,561, which is larger. Okay. By the way, as far as the formula, we are going with this formula. Okay, class. So we can replace the top with the function and the bottom with f prime. Okay. So where do we begin with? Somewhere I would say 2 would be a good place. Again, 2 to the power of 8 is 256. 3 to the power of 8, let me write that for you, class. This one, 2 to the power of 8 is 256. Okay. And in this case, 3 to the power of 8 is 6,560. Okay, so having said that, let's go with 2 and do the math. So x sub 2, okay, equals x sub 1, which is 2 minus x sub 1 to the power of 8, that means 2 to the power of 8 minus 500, 8 times 2 to the power of 7. Okay, so we are showing one step, we are doing step-by-step work, showing our reader what we are doing. Okay, very easy. And that's good enough. It gives us x sub 2. The rest can be done using a calculator. As long as you can do one, you can do all. So here's 2 approaching x, and repeatedly click enter. We want up to 8 decimals class, okay? So take a look, for example, here ends up with 8-1, and the next one 7-6. That's not good enough. We want 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and there is one more we do. In this case, x sub n ends up being this last one. Okay. If you want to go, okay, so that was x sub 2, 3, 4, 5, okay, 6, 7, 8, 9, 10, 11. So x sub 10 and x sub 11 are the same class. Okay. Now, since, okay, all of those, since we want 8 decimals, I want to count it one more time. 1, 2, 3, 4, 5, 6, 7, 8. These two are the same, okay. So 6 decimals. So as you can see, they vary, okay, up to 8 decimals. So from here, we have approximated between the two. I hope you notice this one, when you round it, what do you get, class? Take a look at this one, round this number. 2.1745592.7. You want to stop at 7. How do you stop at 7? You look at number 6, you round it. That's how we end up with 8. I hope everybody understands why 8. We want 1, 2, 3, 4, 5, 6, 7, 8 decimals. You take a look at number 9 and you make the change. And that's your answer. I want to look at quickly one more example, class. Approximating the positive root of this function. Okay, first, again, if you have no idea what the positive, you can start from somewhere. It may not produce anything. As it appears, there are 3 zeros. Okay, this is one of them negative, this is one of them at precisely 0, and this is a positive. So we can approximate the positive root of 3 sine x equals x. Okay, those are the we want the zeros for the root for this function. That means we want the point of intersection. My apologies. What one happens at 0, 0? What happens at this point? What happens? One happens at this point. Okay, so there are 3. 0, 0 is obvious, and the other 2. So you need sort of a graph to have an idea of what's going on. Starting with the function, we take the x to the left, and that becomes f of x. And f prime is 3 cosine x minus 1. And we have the function, we have f prime. Okay, so we want to write this. Okay, so we're going to write that x sub n plus 1 is x sub n minus f, 3 sine of x sub n minus x sub n over f prime over 3 cosine of x sub n minus 1. So we write that, okay, and so x sub 2 would be x sub 1 minus that, let's start with somewhere, and we start with number 2. According to the graph, we see number 2 is close, okay? You can start with that and see what happens. That's the idea, okay? Plug in 2, and 2 is in radians class. So you plug in 2, you get x sub 2 equals 2.323732. Again, a tedious process. If you want to use that again by hand, obviously we put it into a calculator and we get the next one. And right away, notice even the first decimal, they are not the same, okay? And you use a calculator class, again, showing you the calculator. The next one, x sub 4, and the next one, x sub 5, they're almost the same. We are looking at 2 decimals within my apologies, 6 decimals. 6 decimals, everybody. 2.278863. Okay.